All right, so today we're going to be talking about quantum numbers. The electrons in an atom are moving in a constant wave-like motion around the nucleus, so the orbitals are an idea of the location an electron might be in an atom at a given time. More about orbitals. We've drawn orbitals with Bohr models. We know that there's orbitals out there, but actually those orbitals are actually invisible. They actually really don't exist. It's just an idea, a region of where an electron might be in an atom. Quantum theory is important because it helps mathematically describe the properties and location of the wave-like motion of electrons in an atom. And each atom has their own quantum number code to describe the properties and location of the electrons and their orbitals through quantum theory. And there are 4 quantum numbers. The first quantum number we're going to talk about is the principal quantum number. Now, the principal quantum number, their variable for that is going to be lowercase n, indicates the main energy level occupied by electrons. If you remember the last lesson for Bohr models when we talked about orbitals, we said that those orbitals have main energy levels. So whenever we talk about main energy level, we're talking about the orbitals. So in a sense, principal quantum number is the number of orbitals. And we know from yesterday that the number of orbitals equals the row numbers. We know there's never a negative row number, so these values are always going to be positive. So really, n equals the number of orbitals, and we know that equals the row number. And the value ranges for a principal quantum number is going to be from 1 to 7. So let's go ahead and do some practice problems, and we're going to determine the principal quantum number of the following elements. The first element we have is chlorine. Now looking at chlorine, chlorine is in row 3, therefore n is going to equal 3. Now, next one we have potassium. Potassium is in row 4, therefore n is equal 4. Silver is in row 5, so n equals 5. Now looking at uranium. Now, a lot of you guys would want to say that, well, it's row 9, 7, 8, 9. Well, this here actually goes inside here. It's an extension. So elements 57 to 71 inserts right here into row 6, and elements 89 to 103 enters here. And this is what the periodic table looks like if we didn't have this exited kind of taken out on the bottom, if we just had it all together. It's pretty big, so that's why to make it more small, we kind of do it this way. So really, this row is actually in row 6, and this row is in row 7. Uranium is here, therefore row is 7, so n equals 7. Our next quantum number we have is our angular momentum quantum number. And the angular momentum quantum number, and our variable for that is going to be a lowercase l, indicates the shape of the orbital. Now, orbitals aren't always spheres. There's actually 4 different shapes an orbital can be. And the value ranges are going to be from 0 to 3. The first shape that an orbital can look like is what we've seen before, a sphere, a circle. We call this orbital s orbital. Our next one's kind of like more a dumbbell, and we're going to visualize that the nucleus is right in the center here, and we're going to be thinking about these orbitals in 3D. And we call this one our p orbital. Our next one is, let's just say we're putting 2 p orbitals together. Again, our nucleus is going to be in the center. This is our d orbital. And now when we put 2 d orbitals together, this is what it would look like, and this is our f orbital. Now, s orbital, p orbital, d orbital, and f orbital are kind of positioned in a way on the periodic table, where the periodic table consists of blocks. So looking at the periodic table, looking at our elements in groups 1 and 2, and then helium here, all of these is our s block. Now, for s block is s orbital. So anytime we have an element in our s block, L is going to equal 0 always. All of our elements here is our p block. P block is p orbital, therefore L is going to equal 1. Then we have our D block here, and keep in mind we're also including LU and LR because they're really technically supposed to be here in the white boxes. These are our D block, and D block is our D orbital, so L equals 2. And then lastly we have here, these are our F block, and F block is our F orbital, and L is going to equal 3. So let's go ahead and do some practice problems. We're going to determine the angular momentum for the following elements. First element we have is chlorine. Chlorine, we have to figure out what block chlorine's in, and chlorine is actually in P block. And what you just wrote previously, P block L is going to equal 1, therefore L is going to equal 1. Looking at potassium, potassium is an S block. S block L equals 0, so therefore potassium's L equals 0. Silver. Silver is in our D block, and we just wrote that D block, L equals 2. And uranium is in our F block, and F block equals 3, so uranium's L is going to equal 3. And that is our angular momentum quantum number. Now we have our magnetic quantum number. And the magnetic quantum number, which we abbreviate, indicate with variable m, indicates the orientation of an orbital around the nucleus. So as you can see, we have an example of what the S block would look like. We can either have the orbital go up and down, we can have the orbital go on our x-axis or a y-axis. It just depends on the orientation. And the value ranges for a magnetic quantum number is from negative L to positive L. It is dependent on your L value. So it's very important you get the correct L value because it's going to help you get the correct M value. So looking at our periodic table, we have our S block. We know S block L equals 0, so it's either going to be from negative 0 to positive 0, but we never have negative or positive zeros, so M is going to equal 0. Therefore, all of these elements that are in our S block, M is going to equal 0. So now moving on to our P block. We know for our P block, P orbital, L equals 1. Therefore, our ranges is going to either be from negative 1 to positive 1. So let's figure out how to determine those ranges. Well, we're simply just counting. We're starting at the beginning of our row block. And what I mean by row block is row and the first element of that block. So if we look at row 2 for P block, the first element in this row block is boron. So let's start counting here. And all we do from the number line, we start with our negative numbers, then we go to our positives. So we go negative 1, 0, positive 1. Negative 1, 0, positive 1. And you continue to do that. So that means all of these elements in group 13 are negative 1. Then we have 0, positive 1, negative 1, 0, positive 1. That same idea applies to our D block. We know D block, D orbital, L equals 2. Therefore, M is going to be from negative 2 to positive 2, and we'll do the same thing we did with P block, but now we're going to be doing negative 2 to positive 2. So we start at the beginning of our row block. The first element in our block is CS, negative 2, negative 1, 0, positive 1, positive 2, and we would repeat that. Now when you do that for row 6, keep in mind you got to start counting here. These elements actually fit in these blanks, so we go negative 2, negative 1, 0, positive 1, positive 2, and so on and so forth. Same idea still applies for our F block. We know for F orbital, L equals 3. So M is going to be from negative 3 to positive 3. So we go negative 3, negative 1, 0, positive 1, positive 2, positive 3. And then we repeat that step. Okay. So let's go and do some practice problems to find the magnetic quantum number. First example, we have chlorine. We know chlorine from previously is in P block. So L equals 1. Therefore, we have to do from negative 1 to positive 1. We start at the beginning of our row block. We're not starting at sodium because it's a different block. So the first element of row 3 is aluminum. We do negative 1, 0, positive 1, negative 1, 0. So chlorine's M equals 0. Potassium. We know potassium's an S block. L equals 0. Therefore, M is always going to equal 0 for S block. Looking at silver, we know silver is in D block, L equals 2. So we're going to go from negative 2 to positive 2. So we have to start the counting at the beginning of our row block. We're not going to start at rubidium because that's a different block. The first element in our D block in this row is Y. So we do -2, -1, 0, +1, +2, -2, -1, 0, +1. So silver's +1 for M. Making sure when you do M, you have to give me the positive sign or the negative sign. You can't just give me just a number unless it's 0. So always give me the plus sign or the minus sign, whichever one it would be for the answer. Then we have uranium. Uranium's an F block, L equals 3. So it's going to go from -3 to +3. And the first one of that row is AC, -3, -2, -1, 0. Uranium's M is 0. Our last quantum number we have is our spin quantum number. Now our spin quantum number, which is MS, indicates the two fundamental spin states of an electron, meaning is it going to spin up or down, clockwise or counterclockwise? What direction is that electron going to spin when they're orbiting around the nucleus? Our values for spin quantum number is either going to be -1/2 or it's going to be +1/2. Just two possible values. Both of them are going to be 1/2. It's just either you're going to have a negative sign or a positive sign. So looking at our periodic table, we're going to be counting like this. But last one for M, we started at our negative values. But if we're going to do spin, our MS, we're going to start with positive. So essentially looking at our S block, we would start +1/2, -1/2, +1/2, -1/2. And you repeat that until you get to your actual elements. So we're still going to be doing that counting. So let's go and do some practice problems of determining the spin quantum number of the following elements. First, we have chlorine. Again, we're going to start at the beginning of our row block, so it's going to be aluminum. So we're going to do positive, negative, positive, negative, positive. Therefore, chlorine is +1/2 for MS. Looking at potassium, starting in our row block, that is potassium, and we always start with the counting of positive, so potassium's +1/2. Silver, starting at the beginning of our row block, Y, positive, negative, positive, negative, positive, negative, positive, negative, positive. Silver is going to be +1/2. Then lastly, uranium, beginning of our row block, AC, positive, negative, positive, negative. Therefore, MS is -1/2. Just like I said for M, for MS, if it's a positive, you got to give me the positive sign. And if it's a negative, you have to give me a negative sign. I need not only the half, but also that sign, the positive or negative sign. So those are our 4 quantum numbers. Let's go ahead and put them all together and do some more practice problems. You're going to determine the 4 quantum numbers N, L, M, and MS of the following elements. Go ahead and do this on your own. So you're going to go ahead and pause the video, do it on your own, and when you have your answers, press play so you can check them. And here are your answers. And that is quantum numbers.